Greetings! In this video we are going to present our research work called the Air Quality Index forecasting using machine learning methods. This work has been jointly developed by members of the Modelado Inteligente de Sistemas research group of the University of Cádiz and the Grupo de Inteligencia Computacional Aplicada of the University of Burgos. As we all know, human beings and living creatures need air to survive. However, this air can become harmful due to the presence of air pollutants in concentrations above certain levels. Air pollution is a complex phenomenon which can involve different substances. Each of these substances has its specific way to be measured and legal limit. As a result, understanding all the details and measures can become a rather tricky task. Through the Air Quality Index, all these heterogeneous measures are simplified in a unique index much easier to understand and use. The Air Quality Index is used by the governmental agencies to inform about the current pollution levels. It can also be employed to indicate the levels that are foreseen in the near future. As this index grows, more and more people are at risk of suffering health problems. Due to the effects of air pollution in human health, obtaining accurate predictions of the air quality has become an essential task for governmental agencies. Forecasting air quality models can be advantageous to take preventive measures to ensure the well-being of the population. Additionally, these models can also be used to provide useful information about environmental quality and others. In our work, different models have been developed to forecast the AQI using machine learning and deep learning techniques. The area where all the experiments were held is located in the Bay of Algeciras, in the south of Spain. This is a very industrialized and complicated scenario, which includes several factories and one of the top ports in Europe. The use in this study has been provided by the Environmental Agency of the Regional Government of Andalusia. It includes hourly measures of PM10, PM2.5, CO, NO2, O3 and SO2 taken from 2010 to 2015. You can find different ways to calculate the AQI. Among them, we have selected the indication of the EPA, United States Environmental Agency, which is one of the most recognized standards worldwide. AQI is created based on the measures of 5 different pollutants: CO, NO2, O3, PM10, and SO2. The AQI is calculated based on ppm or microgram per cubic meter emissions, using different periods and moving averages depending on the pollutant. Its scale ranges from 0 to 500 and is divided into 6 categories. These categories classify the air quality from good to hazardous. The higher the scale is the category, the higher the risk it represents for human health. Now we go on to give a brief description of the methodology that has been followed. In this work, we have employed 3 different techniques to create the forecasting models: artificial neural networks, support vector regression, and LSTMs. Inspired by artificial neural networks are computational models inspired by biological neural networks that have been used in many different areas to inquire about the complex nonlinear relations between predictors and dependent variables. A typical neural network is composed of a number of artificial neurons called units, which are arranged in different layers and linked by synaptic webs. Feed-forward multilayer using map propagation is the most popular and widely used design for artificial neural networks. Its architecture is composed of an input layer, one or more hidden layers, and an output layer. The network is organized in fully connected layers, with information going forward and errors being propagated backwards in a supervised learning procedure. In this work, feed-forward backpropagation neural networks have been trained using Levermer Marquardt as the optimization algorithm. To avoid overfitting and poor generation performances, the artificial neural network models were trained using the early stopping technique, and different number of hidden units have been tested from 1 to 50. Vector regressions, SVRs, was the second technique used to create the forecasting models. SBRs can identify linear and not linear relationships between inputs and outputs as they approximate an unknown function to map the input data into a high-dimensional feature space. It is important to note that the performance is heavily dependent on the kernel that is employed. In our case, the Gaussian kernel was selected. The third forecasting method that was also employed in this paper was the long short-term memory neural networks, LSTMs. Sequence structure including 5 different layers, a sequence input layer, a LSTM layer, a drop-off layer, a fully connected layer, and a regression output layer. Regarding the parameters used, the number of neurons present in the hidden layer, the initial learning rate, and the dropout rate were determined through Bayesian optimization. The remaining hyperparameters use their default values. Additionally, the Adam optimizer was employed and the number of epochs was set to 200, with early stopping set to 25 values. Experimental procedure. Continue with the experimental procedure. It's important to note that the database was normalized and was divided into different groups. Training groups including records from 2010 to 2014, and a test test set, including records from 2015. Regarding the forecasting approaches that were used in this work, we have two different steps. In the first one, we made the forecasting of the concentrations of each pollutant 8 hours ahead. For that, we used different sizes of autoregressive windows, 48, 72, 96, and 120 hours. And we applied a resampling procedure with two-fold cross-validation. In the second step, we obtained the future AQI with the predicted concentrations. In this new slide, we can see the results obtained for the step 1 forecasting approach. As we can see, the performance indices that were used were the RMSE and the MAE. The most important thing to note here is that the best results for the pollutants are obtained using the artificial neural networks, and that the LSTMs in some of them is fairly close to the results given by the artificial neural networks, but in others it's like in the middle of the results obtained by artificial neural networks and SBRs. In contrast, SBRs are always giving the worst results in all the cases. Forecasting approach, as we can see in the figure, the fit between the observed AQI and the forecasted AQI, no matter the method used, is really good. An important thing to note is that the performance of these step 2 methods is far superior than the performance obtained in the step 1 approach. A procedure to forecast with general conclusions. This work we have presented the newest two-step procedure to forecast AQI values with 8 hours in advance. The experimental results indicate that artificial neural network performance was slightly better than the performance provided by the LSTMs, and better than overall than the performance obtained using SBRs, and that this study can be a very useful tool to detect the values of AQI with time enough to activate defensive protocols against high air quality episodes. And finally, as the future work, we have to say that we are working with a new extension of the methodology presented in this paper using bidirectional LSTMs, and that the results that we have obtained up to date are really promising.